Now we look at a situation where the characteristic polynomial gives us repeated real roots. So let's take as our example y double prime plus 4y prime plus 4 equals 0. Okay, then the characteristic polynomial for this one is going to be r squared plus 4r plus 4. And this one factors into r plus 2 quantity squared. So we end up with roots minus 2 and minus 2. And so then that tells us that for we get one solution, e to the minus 2x. But what about y2? So we know that we can't take a scalar multiple of e to the minus 2x because, like the example that I did a couple video clips before, given the initial conditions, we might not be able to solve. In other words, the solution space of this differential equation is two-dimensional, and we cannot span it with just one single function. We need two things for a basis. Okay, so what are we going to do? Well, general rule of thumb, slap an x on it. So we'll just multiply the one that we had before with an x. And at this point you say, what? Why? Where the heck did that come from? Okay, so here's the full story. The short version is you can always just do this, and then your solution will work. Sometimes this is written, they factor out the common portion. Okay, but that's highly unsatisfying, right? So where does this come from? Okay, so the idea is to look for a solution of the form vx e to the minus, well actually, in general, vx y1 of x. So the idea here is to let the parameter c1, the coefficient, and for y1, vary. In other words, replace it with a function. And so this is what's called a reduction of order technique. We'll see that this ends up reducing the order. So if we make this substitution, if y is v e to the minus 2x, and we substitute that into the equation, then let's see. Well, we're going to need y prime. So y prime is v prime e to the minus 2x minus 2v e to the minus 2x. And we're also going to need y double prime. And so y double prime is going to be v double prime e to the minus 2x minus 4v prime e to the minus 2x plus 4v e to the minus 2x. And so substituting all this in, to the original differential equation, we are going to have, so let me grab a copy of y double prime, so that's this guy here. And then I'm going to have plus 4 times y, so that's this guy here. And then I'm going to have plus 4y. And this is all supposed to add up to 0. Okay, and then we have some beautiful things going on here. So let's see. So if we look at the v e to the minus 2x terms, there's 4 of them here, and 4 of them here, and minus 8 of them right here. So bam, bam, bam. Those guys cancel. And then if we look at the v prime e to the minus 2x terms, there's minus 4 here and positive 4 here. So those ones are gone as well. And so this whole thing then just boils down to v double prime e to the minus 2x equals 0. But it's not the exponential that's 0, so it must be v double prime is equal to 0. And we can find that just by integrating. So if we integrate that twice, v looks like c1x plus c2. And so then that tells us that our y should be c1x plus c2 e to the minus 2x. And so part of that duplicates what we already have, but one way or the other we still see that we have 2 degrees of freedom now. And so we get that y looks like c1x plus c2 e to the minus 2x. And so it works. And in the future, you do not have to rederive this part right here. You can just skip right to the end with the good part and just slap an x on it. Call it good.